Okay. What I like to do is kind of go over the midterm project, as I mentioned before, that I wrote the final exam. Now, I don't know if the final exam questions are final or not because they're going through a review process and things like that, but I have a pretty good idea looking at last final and what I wrote for this year, what's going to be on the final. So I wrote this midterm with the idea of, preparing you for the final exam and that there. So we've got some questions here that there. The first one, and I'm not going to type these answers, I'm just going to give them verbally and kind of point out what the key points here. If you look at the Bride book, the 8086 are covered in the same book. They're talked about as if they're the same processor. They are basically the same processor, but there are some very important differences. The number one important difference that I would be looking for is that the 8086 is a 16-bit microprocessor internally and externally. The 8088 microprocessor is a 16-bit microprocessor internally, but externally it only has 8 bits. So when you look at so it takes twice as long for doing memory accesses and things like that. So the 8088 is a slower microprocessor because it only has 8 external data bits. That's there. So that is a key difference that I'm looking for. That's there. Internally, they have the exact same register component. They have the exact same clocks, but the major difference is that the 8088 is an 8-bit microprocessor externally. That's there. And the key part of that answer is that if you tell me that the 8088 is an 8-bit microprocessor, you're going to lose half the points for that particular problem. Because the 8088 is a 16-bit microprocessor internally, an 8-bit microprocessor externally. So that is what we're looking for, and I don't remember how many points that I assigned that for that there. The answer marked out of 5. So the number of points assigned to these problems are relative to what that there. So that there. The next one here is I just simply cut and pasted a picture of the 8086 there, explain the purpose of the following pins. Let me just go through it, and again, I'm going to answer these verbally. I'm not going to type the answers up that there. The clock, of course, is the clock for the microprocessor. It synchronizes all operations of the microprocessor. You don't have to get into much more detail on the purpose of the clock. It is a system clock. That there. The INTR is an interrupt request line. This is a maskable interrupt request going into the 8086 right there. The NMI is a non-maskable interrupt request line. So these are the interrupt request line and the non-maskable request line. That's there. So that's the purpose of that pin right there, is that the interrupt request is anytime a device requires service externally, it would flag the interrupt request. I didn't ask the process, but then the microprocessor would then go back and ask what interrupt it is. We did not talk about the interrupts in great detail on the 8086 or 8088 family, but you should know what the interrupt request line is. The NMI is a non-maskable interrupt. That there. So this is an interrupt request that cannot be masked. Later on, there's another question: was what's the difference between a mask and a non-maskable interrupt? Right there. RST is the reset. It resets the microprocessor back to program counter back to 00, and that there. And then the RD is the read not line. That's taken as part of the read cycle right there. So really, for the answer to this, what you basically need to know is what are these pins. You don't have to go into great detail and give me a 3-page explanation of what happens with an interrupt request line. This is just it's a maskable interrupt request. Very simple answer. Yeah, and this problem is worth what is this worth? 5 points. So we're talking 1 point each. So I'm not looking for a 3-page dissertation on any one of these answers. Just a very simple that you know what these pins are. Clock. the system clock used to synchronize all the microprocessor. Interrupt request, and a maskable interrupt request line. NMI, non-maskable interrupt request line. Reset, used to reset the microprocessor. That there. Read dot, this is the read dot line, taking load during the read cycle right there. That's all you need to have for that there. So, as a matter of fact, as I recall, I pointed to a section in the textbook that there where it lists all the pins, and they had about 2 sentences on each pin. I said that's really what you needed to know. So if you looked at, if you've ever, now keep in mind that there's a lot more pins I can ask about. That's there. So as you look at this right here, I picked, actually, because I do ask about the 80-0 and 80-15 later on. Okay, same picture. Explain what is meant by multiplexing 80 zeros to 80-15. Okay, I'm still talking 80-86 there. Right there. 80-0 and 80-15. These are the address and data pins. So when you answer this, I'm looking for something on the line is that for some of for a period of time during the read or write cycle, these lines will contain the address lines, the data. At other times during the read or write cycle, it will contain the data that's being read or write. So what we're looking at is the fact that these lines represent address part of the time, data part of the time. That's there. So I spent a lot of time going through the ALE and what these functions do in the interface. So I would expect that you would know that these lines, what is expected by multiplexing is that these lines are used part of the time for the address, and then part of the time for the data. And there's a cycle that we go through, and later on you're expected to tell me what's happening during that cycle, right there. So this is all leading up to the same basic understanding. Again, I don't remember how many points I put on this one. This one is also 5, but this is 5 points out of 1 question. So that's 1/20th of the right there. That you would expect. You're expected to know what those 16 pins do. Now, if I was talking the 80-88, it would be 80-0 through 87, right there. So again, what I'm looking for was meant that they're part of the time. These 16 lines contain the address. Part of the time that contains the data, right there. All right, this here is just, again, this is 5 points again. That there, explain the difference between a maskable and a non-maskable interrupt. The name itself tells you what the answer is. You can program the microprocessor to ignore a maskable interrupt. You cannot a non-maskable interrupt. You can, that there. That's all you need to say is that the difference is a maskable interrupt, and mask is misspelled. There shouldn't be a D, ED there, but there. But a maskable interrupt is one that you can ignore. That there, and again, that there, where a non-maskable interrupt must be serviced. That there, I can go right into on the 80-51. I can enable my interrupts or not enable my interrupts. That there, but a non-maskable interrupt is always enabled. That there. Get an example of an interrupt you might want to mask for a period of time, or one you don't, and one you don't want to mask. That there. So again, an interrupt that you might want to mask is, for example, the temperature of a particular, the flow rate of, say, a gasoline pump. One you don't want to mask is the shut-off valve on a gasoline pump. That's there. A missing signal on a heart rate monitor. In other words, I'm looking for an example of something you might want to mask at certain periods of time. You might want to ignore the temperature in a room right there while you're doing other things. but you wouldn't want to mask a fire sensor. So there's 100 answers for B, right there, 100 different answers. I leave it open, that's there. So it's, again, and the interrupt that you would want to mask, it could be anything you can mask. Again, you could use your phone. You mask certain phone calls. I don't know how many people turn their ringers off at night when they sleep. I definitely turn my WhatsApp ringer off at night. I don't want to hear any WhatsApp beeps at 2 in the morning because I belong to a couple of groups that like to send messages at 2, 3 in the morning for whatever reason. I don't want to read that stuff at 2 or 3 in the morning. It's not important. But I definitely would not want to say, for example, if I'm traveling, mask my wife's phone number. I may want to mask my ex-wife's phone number. That's there. So, okay. Answer C, what is the role of the interrupt vector table and the interrupt service routine? That's really two different questions. The interrupt vector table contains the address of all the interrupt service routines for the various. Is this thing turned on? Right there. Right there. Okay. If I don't, is this thing plugged in? No, it's not plugged in. Okay. Yeah, okay, now it shows it. If it's unplugged after about 2 or 3 minutes, it shuts the screen off to save battery. Okay, the interrupt vector table contains the address of the various interrupt service routines that are there for each of the interrupts. The interrupt service routine is the code that is written to service a particular interrupt. That's, again, short answers. As you look at your project that you're doing, you're writing the service routine to service interrupt, the timer interrupt. Right there, that's the interrupt service routine, the ISR. The interrupt vector table is where the address of that routine is placed in the interrupt, whenever that is called. Now, most people remember the interrupt service routine more than the interrupt vector table because if you're writing in C, you typically don't worry about putting the address in there because you label that as interrupt 14 or the name of the interrupt right there. And the compiler automatically puts the address into the interrupt vector table. If you're writing into assembly language, if you recall, we had to put the address there. That's there. And I'm not going to go through that example. I don't want to get sidetracked. I just want to answer these questions up there. But the role of the interrupt vector table contains the address of these interrupt service routines. The role of the interrupt service routine is to actually process, to handle the interrupt. That's there. To do something, what you want to happen when this interrupt occurs. That's there. And then we go to our next question. Right there. We get here to 5. Right here, 5 is the one that you can't see the whole thing, but you can see enough of this right there. And right there is explain the function of the 74LS373. All right, an LS373 is a octal latch. Right? A latch. Fed into it is on the gate is the ALE, the address latch enable. So the role of the LS373s or 74LS373 is to latch the addresses. What is the role of the ALE? Is the ALE is high when there's an active address there. So the ALE tells the 373 when to latch that address. Because if we were to look at this whole thing, which we can't see on this particular one here, what's shown on the right is the addresses. And what's shown down here is 80 through 87. What's shown off to the right on the bottom is those are the data lines. But what comes out of the 373, again, I apologize because the screen resolution doesn't let me see the whole thing, but if you look at the whole picture, you'll see that on the right, you'll see A19 to A0 without the D there. That means that this ALE goes high, that tells us 373 that there's a valid address, and when the ALE goes low, the address is latched onto that there. So the role of the 373 is it holds the address on its output. That's there. The role of the ALE is to tell it when to grab the address. So the 373 are used to latch the address, to separate the address lines from the data lines. Right there. So that's the answer I'm looking for, something along that line. The 373 is used to latch the address. The ALE tells it when to latch the address. So the two of them work together right there. Right there. Explain how that's there. Explain in this circuit above, explain the function. It latches the address. The ALE, how does this line come into play? It tells it when to latch the address. Right there. So as you can see, there's a lot of questions on this memory interface. This is a big deal. This is probably the last one. What is happening to the ALE during this memory write cycle? Right there. And I can't do it here, but what's happening is the ALE is going to go high sometime during here and go low during this time period right here. See this address line right there? When that address data line is shown is a valid address, the ALE goes high and then it goes low again. And that is used to latch the address. So as we go through these questions, you can see how important I think it is that you understand how we interface this any microprocessor to memory. That's there. Because again, that's the hardware part of it. That's the most difficult part of the hardware. That's there. So, and by the way, this here, a little hint as you look at a final exam, in any final exam, if you see a question you don't have to answer, it might help you to read the rest of the final. You might see some hints. Right here's a huge hint to the question: is what is meant by multiplex. Huge shows exactly what multiplex is. Matter of fact, if someone drew this drawing as an answer to that question, I would accept it. Because this shows that this is AD0 through AD. I shouldn't point to that there. I should point over here. This is AD0 through AD15 in that question. It's addressed during this part of the cycle, right here, and this data here. Now this says valid address here. That valid address is after the LS373s have latched it on. Right there. So these are the lines coming from the microprocessor right here, AD0 through AD7 or AD0 through AD15. It's a valid address here. The ALE goes high somewhere during this period and goes low again. That's what you need to answer right there. It goes high and low. As a matter of fact, I would say that chances are you would be asked to draw this on a final exam. Draw what the ALE is. That's there. So it would go high during the time between here and here. It would go high and then low again. It would just simply pulse high and low, and that would then latch the valid address onto the output of the 373s there. So when we look at this drawing, it all equates back to the previous ones. Right here. Okay. Here, what is the memory organization of this device here? What we're looking for is the number of bytes times how wide, or number of memory locations, the size of each location. We look at this here, we've got 0 through 07. Since I'm recording this, let me sit down so I can. But the reason I want to sit down is because pointing to the screen is better for, public speaking. They say that you shouldn't sit down and talk to the computer, but since I'm recording this, it makes sense to show the arrow here. but we've got these lines 00 through 07, so that tells us that we've got, this is a by 8, right there. And we've got our address lines, we've got here, we start here with A0, and we go to our top one is A11. So, 2 raised to the 11. This is a 2K. This is a 2K by 8 right there. Is what the answer would be for this particular problem. So there's, roughly 2,000 memory locations, and they're each 8-bit wide. And I can tell that by looking at this right here. Right there. And there's a little bit of a hint right there. This here, and I don't guarantee that I would make this mistake on a final exam, that I would put the part number on the top there. But this is a 27C32, so that means it's 32K bits right there. So that agrees with the answer. But don't use that as your study guide, because I don't guarantee that I would leave that on the question on a final exam. What you should look at is the number of output lines right here, and they may be labeled as I/O, or it may be labeled as output. This happens to be a ROM chip, because they're labeled as output right there. Later on, there's another question where I ask you to identify whether it's a ROM or RAM. That's there. This one hint on how to tell that it's a ROM is that these are only outputs right there. There. So, and then the number of locations is determined by looking at the number of address pins. So I found 2K by taking the fact that I've got A0 through A11. That means there's 12 actually. Right there. What did I say? It should be 2 raised to the 12. 4K, excuse me, that there. It's a 4K. I made a mistake. That this is a 4K by 8. Because there's 12 address lines. So you look at the number of address lines, since 2 raised to the number of address lines gives you the number of locations. So there's 12 address lines. I said 11 before. That's there. So I would have lost myself 2 points on that one. That there. All right. Explain the purpose of the following pins. Same type of question. O0 through A7. It's the same chip actually. And these are the OX. Those are the output or the data lines. That there. The CE0. That is the chip select NOT. That is taken low when this chip is selected. And the AX are the address lines right there. And by the way, this one was worth 10 points. So this is an important question. So you need to recognize what is the purpose. These are the output lines connected of the memory device. They're connected to the data lines. The chip select is low when this chip is to be accessed, and this is the address within the chip right there. Okay, excuse me as I scratch my ear. Okay. These things sometimes itch after a while. Okay, hopefully we get this. We can get okay. This again is a chip right there. What type of memory device is this? And I can't, that there. And this is a RAM device. The reason I know it's a RAM is that there's multiple ways that you can answer this, but this is a RAM. Why did we answer this? Is that we have 2 lines here called write enable and output enable. That means that we can read or write to this chip, which means that it's a RAM. That's there. And we also have the input and output lines are labeled as I/O NOT. So this is a RAM. So there's two ways that we know that. One is that the fact that we have 1 line for output enable and 1 line for write enable. So we would put, this chip would be selected using a combination of chip select 1 and 2. This has 2 chip selects right there, and they both have, one has to be low and one has to be high for this chip to be selected, right there. And I think that's part of the, right there, actually, I have a mistake there, but again, there's chip select 1 and 2. They both have to be active for this chip to be selected, right there. You know, the only difference is, in the way I worded the question, there is no difference. But if you look at the actual chip select 2 has to be high and chip select 1 has to be low, that there. But they both have to be active in order for this chip to be selected, right there. So there is essentially, they're treated as equal pins internally, right there. All right, getting back to the top of the question right there. Right there, you know, so what type of memory? It's a read-write memory or RAM. Why did we answer that way? Because it has the data lines are connected to pins labeled I/O instead of just output, and we have a write enable and an output enable pins. So if it's going to be used as if we're reading this memory, we would take the output enable low. If we're writing to this memory, we would take the write enable low. So that's how we talk to this chip right there. So what is the memory organization of this chip? Same thing. We have 8 I/O pins right there. So it's a by 8. Our address lines, it looks like we've got the same number of address lines. Actually, no, 13 address lines. So we've got A12, and we start with A0. So 13 address lines, it's going to be an 8K by 8. So we use 2 raised to the 13 is 8K right there. So again, what we're looking at right there, the memory organization there is we look at the number of address lines tells us how many locations we have up there. So you have to be able to do that. Again, I have no idea what chips I'm going to use. Don't expect it to be these same chips, but expect a problem that's going to be similar to this right there. So this particular chip has A0 through A13, or A12, excuse me. That's 13 address lines. So 2 to the 13 is 8192, or 8K, right there. So we just simply, and you're allowed to use a calculator, just 2 raised to the 13. There's my 8K right there. And by 8, and the reason I get the 8 is that I've got IO0 through IO7 right there. Now, a little hint is that when we look at memory devices, they normally come in one of 3 different flavors. They're either by 1, in other words, you only have 1 output right there, or they're by 4, or they're by 8 right there. So far, we've only talked about by 8 right there. But if you look at a lot of the desktop PCs, you might see that there's, 16 chips across there. That's a 16, and each one of those are 1 bit by a lot of memory locations. It might be 16 gig by 1. That there. So you have a lot of combinations. You might find some by 4, but again, all you're looking for is how many lines are connected to the data bus. In this particular case, you've got 8 lines. In my previous one, they're labeled as output. On this one here, they're labeled as I/O. The I/O means that it's either an input or an output, but they're still connected to the data bus. So that's there. And again, what's the difference between CE1 and CE not is they're both chip selects and both have to be active. There is no difference internally that there. Now the only difference is that if I would have left that not there is CE1 has to be taken low and CE2 has to be taken high, but they both have to be active. So from a practical standpoint, there is no difference. That there, other than if there's a knot in front of one and there's not one between the other one, then it's taken half. But they both have to be active. Is what is really the key to this question. That there, because sometimes we use these chip selects as part of our addressing scheme. Right there, explain the purpose of right not and output, or right enable not and output enable not. Again, I talked about that a minute ago. During a write cycle, the right enable line is taken low. During a read cycle, the output enable is taken low. That's how the chip looks at the difference between a read and a write cycle. Right there. So I didn't ask you to draw the timing pattern, but that timing pattern is actually in the Bride book. We talked about that early in the semester. But that's how we determine whether it's a read or write. Right there. The purpose is that there. So a write enable, that there. Okay, this is one that I can't go through this particular one because I can't show it. This is an important one. I think this one is worth 15 points. This is a very important one right here. The circuit that there, address selected, modified to select the range. Now, we can look at this easily enough right here that there, I can see enough of this to solve the problem. Right there. Right there. Because we've got 8 ROMs here, and what we've got coming into this here is we've got right here, these 4 lines have to be high for this 138 to be selected. This is what this chip right here is, the 138 is a 3 to 8 decoder. So let me just talk a little bit about this particular problem, because this problem is a big problem. I know it was in the homework I gave earlier. It shows up again here. This is one that will cost people some points. I know right off the top that not everyone's going to get this problem right. There will be something like this on the test. So let's look at this particular problem right here, and let's talk about it here. Right here. Okay. This is our 138. This is a 3 to 8 decoder right there is what that is. It's got 8 outputs right there. Now, these outputs are going to, and we have 3 inputs, A, B, and C, right there, A, B, and C. Right there. Now, depending on how this is hooked up, and I don't know if, all right, this is hooked up with A15 being the most significant right there. C is the most significant right there. So this is A15, this is A13, A14, and A13 right there. Is that right? All right. So what this is saying is that if this chip is selected, and we'll talk about selecting this chip in a second here, that there, if these 3 are 0, then this one's going to be a low, and these are all going to be high, right there. So if this is 0, 0, 0 right there, that means that this chip is going to be selected right there. If this is 1, 0, 1, in other words, the number 5, that means that 0, 1, 2, 3, 4, 5, this one's going to be a 0, and the rest are going to be high. So in other words, it's going to look at this number and take one of these low. Is the way this chip works. Now that is not the key to this problem. That tells me what happened. That will tell me which chip is selected if I ask that question. That there, and that there. But you need to understand the circuit completely. That's there. This is what there. Now, what this circuit, if going back to this circuit right here, I've got, on this circuit, I've got 3 chip selects right there. Everyone see the 3 chip selects? G1, 2, and B. Or G1, G2A, and G2B. All 3, just as in the previous problem, that both those chip selects had to be active. All 3 of these chip selects have to be active in order for any of these outputs to be low. This chip has to be selected. That's the key part of this problem right here. Now, G2 is just tied to ground, so we're not using it. We can ignore G2. G2A. G1 is tied to A16. G2B is run through a NAND gate right here. This is a NAND gate that 17, 18, and 19 have to be high. So in order for this chip to be high, or be selected, A19 through 16, all 4 have to be high. And that's what I say right down here. The address selected in this chip is F000 through FFFFFF. In other words, I'm telling you what this chip is selected for. So I'm looking at A19 through A16 is the top 4 bits of the address. Now I'm saying I want you to modify this circuit to where instead of starting in F, we want to start at 4, right? So we want to go from 40000 to 4FFFF. So for that to happen, right here, so we got G2A, that's tied to ground. We're going to leave that there. A16 is going to G2. And if we can get this right here. And I don't know how well this is going to work, but all right. Did I lose? Okay, there we go. All right. Okay, as we look at this right here, so A16 goes to G1. And I keep breaking this right here. Did I lose it? No. I accidentally closed the window here. We got to go back to it. Right here. Trying to okay. And continue the last preview. It should take. All right. Okay. All right. I'm not going to try to get both on the screen. The screen resolution is too poor, and I'm going to end up closing again. But let's try to remember what we've got here. G2 is both active low. G1 is active high. So G2B, G2A, those both have a bubble on them, right? And this is G1 right there. It doesn't have a bubble. Now this one is tied to A16 right there. A16. This one's tied to ground, so we can ignore that one. this one is tied to an inverter right, or a NAND gate right there, right? And this has got A19, A18, and A17 right there. Now, so right now this is set up to where A19 through A16 are 1, 1, 1, 1, or F, right? That's the way this is configured right now. Your problem is now I said I don't want that. I now want this thing to go from 0, 0, 0, 1, 0, 0 right there. So what that is going to involve is that we're going to change. We want A19 to be a 0, A18 to be a 1, A17 to be a 0, and A16 to be a 0. So really all we do is we're just going to add 3 inverters to this problem. It's worth 15 points, and the only key is knowing where to put 3 little square triangles to answer this problem. So we want an inverter here, we want an inverter here, we want an inverter here. We want to change this to where A16 goes through an inverter right there. A17, this is 16, 17, 18, 19. Those are our pins right there. A17 goes through an inverter right there. A18 does not go through an inverter. And A19 goes through an inverter right there. That's the change you have to make to this problem right there. Right there. So as we look at this right here, circuit right here, right there, uses that there. The addresses selected in this circuit are A or F0000 to FFFFFF. Modify this to change that range. The only change you have to make are on these 4 lines right here. You place an inverter here, you place an inverter here, you don't place an inverter here, and you place an inverter here. That is the way that you change this problem. Now, it seems like a very simple answer, but I can guarantee you that the only way you can know where to do this is to understand the way the circuit works. The solution is simple once you understand the circuit. Right there. Now, the other thing is that I also, in the homework, I gave you a very similar circuit, only I left these off, right? And I ask you, so you may find a problem where I ask you a particular memory range of one of the 8 2716s that are sitting there. So in other words, this uses 8 2764s right there. So again, there's 8 chips here. I may leave these addresses off and ask you what the address range of a particular chip is. But you need to understand this circuit and how it works. 15 points, so if you look at this being worth 15 points, you get 3 problems like this right, you pass your final exam, right? Mm-hmm. So that's there. And I can guarantee that there will be something like this. Because this particular problem tests you on everything there is to know about memory decoding right there. Right there. So you will see a question that looks like that right there. Okay, getting now back to the easy questions. And question 10 is not an easy question. That's there. That's probably the ones you struggled with, right? And I'm telling you that you need to understand that problem because it will show up. And that there. The difference between a microcontroller and a microprocessor, there's basically 3 differences that I'm looking for. One is that a microcontroller has built into the IC itself RAM, ROM, and I/O interfacing, clock generation. A microcontroller typically uses more ROM than RAM, and a microcontroller typically is used in some type of control application. So those 3 points there is what we're looking for. Is the main difference is that a microcontroller has built into it everything you need for a complete system. That's there. A lot of the new microcontrollers are actually referred to as a system on a chip. Right there. So, because it has everything you need in one chip. If you look at the 8051, which we're using for the lab, what are we interfacing to that? Nothing, right? Just our input and our outputs. We don't have any external memory. We don't have an external clock. We don't have any external I/O interfacing out there. It's all built into the chip right there. So we're looking at that right there. Okay, these here, I put this drawing up there for you. Right there, that's there. You'll see that there are multiple clocks right there. I put this drawing there. Actually, this drawing has absolutely nothing to do with the answer, other than I just simply say that you'll see that there are multiple clocks available to be selected. In this particular case, we've got a external or a low power clock, 24.5 megahertz low power oscillator that's built into it. We also have a 80 kilohertz low frequency oscillator. And we also have an external clock. And I asked basically 2 questions. Give the reasons you might want to use the external clock. I've mentioned this multiple times. The internal clock is only accurate with plus or minus 20%. So if you need more accuracy, you have to use an external clock. Right there. The part B, the 80 kilohertz low frequency clock, right there. And the reason is that power consumption goes up exponentially with frequency. So if you want to go into a low power idle type mode, you use the low frequency clock to conserve power. Would be the answer you're looking for that there. There are other answers, but those are the key ones up there. What is the purpose of the watchdog timer? And again, I've mentioned this multiple times, is to reset the processor in the event of a software or hardware failure. Right there. Give at least one example where the watchdog timer is necessary. I've repeated the one multiple times of the gasoline pump that won't shut off. Right there. It could be a heart rate monitor. Right there. Or I shouldn't say a monitor, a heart rate, a pacemaker. You know, is everybody familiar with what I mean by a pacemaker? It's a little device that they embed in some old person's chest. That it doesn't have to be an old person; it can be a young person. That their heart seems to forget to beat at times, and it gives a little electric signal to the heart to tell it to keep beating. You know, it's called a pacemaker. Obviously, you would want a watchdog timer and something like that. Any situation where it could be a life and death situation. It could be the controls for a jet aircraft engine. Obviously, you don't want that jet aircraft engine to just shut down or go to full throttle without any control from the cockpit, right? So there could be 100 different answers for Part B, right there. All I'm looking for is that you come up with a situation that is either life or death or very critical that you definitely need the watchdog timer. Right there. All right, this one I really didn't talk much about, but that a nested subroutine is a subroutine that is called within another subroutine. Right there. A recursive subroutine is one that calls itself. Right there. So but again, you need to be aware of these 2 terms. But a subroutine is one that calls another subroutine. So there's a call nested within a subroutine. A recursive subroutine calls itself. You know, to give an example of right there, since I haven't talked about it, let me just give an example real quick, and I don't want to spend right there. Equals 5 times 4 times 3 times 2 times 1, right? 5 factorial. Has everyone seen a factorial, right? Well, that's the same thing as 5 times 4 factorial, right? So I could write a subroutine called int, called factorial. I pass it an integer, x, right there. If x not equal to 1, return, oh, what did I do there? Return x times factorial x minus 1, right there. Else return 1, right there. So I've written a very simple routine to calculate the factorial of x, right there. So all I'm going to do is, if x is equal to 1, I just return 1, because 1 factorial is equal to 1. If it's equal to 2, it's 2 times 1 factorial. If I pass it 5, it's 5 times 4 factorial, right there. This is a recursive routine because I'm calling itself right there. That's a recursive subroutine, right there. So I don't know if you're taught that, and the only reason I ask that is because later on that has major repercussions on how large your stack has to be. Because whenever we call a subroutine, we push the return address onto the stack, and if we call the same subroutine 50 times, we need a stack large enough to handle 50 calls right there. So, right there. So this is a question that I did not cover in class, but I just covered it real quick right there. So, what is the function of a stack during the function call? We push onto it the return address, right, and we pop it back off. That's where the program counter is stored. It's pushed onto the stack during the call, and on the return, it's popped back out. Now, on the return from interrupt, we also pop out the register set as well. What is meant by LFIO is last in, first out. A stack is whatever we pushed onto it last. In other words, we pop things on in reverse order. Right there. So let me review that again real quick. I know that I talked about it, but here's the stack right here. Right here. If we push A, we push B, we push C, it's going to be, we push A, B, C, so it's going to be A, B, C. The last thing we pushed on is at the top of the stack. We pop it out in reverse order. Pop C, pop B, pop A. In other words, last in, first out. Right there. I look at it, it's not, they don't have them here, it's very uncommon. The little paper cup holders that you push them on, you push on that they're, whatever you push, put on last is the first thing you pop out, right there. So it's the reverse order, right there. So last in, first out is what that means. So the last thing we pushed in is C. The first thing we're going to pop is out is C. Last in, first out. Now remember that I'm showing this ABC, is if we did this, if we did push A, push B, push C, and we did a pop A, what that's going to do is going to take what was in C and put it into A. Right there. So it's going to generate an error. Right there. That is, if we want to restore things back to the way we were. If we want to reverse them, we can do that. That's there. But whatever we put in last is the first thing we pop. That's there. With the stack, you have no control of where in the stack. You're always pushing onto the top of the stack and popping off the top of the stack right there. So going back to our quiz right there, what is meant by last in, first out is what that means. The last thing you pushed onto the stack is the first thing you pop off right there. Give the sequence of events that occur when a processor processes an interrupt. These are outlined in the book. I'm just going to try to recite them off the top of my head. That there, you may want to refer to the book there. The first thing it does is it finishes the current instruction, and then it pushes onto the stack the registers so that it can restore things back to where they were. It then pushes onto the stack the return address so it knows where to come back to, and then it loads into the program counter the address that's listed for that particular interrupt in the interrupt vector table in order to execute the interrupt service routine. So it goes to the interrupt vector table and gets the address of the interrupt service routine. That question was earlier in the test, right there. So a lot of these questions get repeated. That's there. So it executes the interrupt service routine. When it comes to the statement return from interrupt, it will then pop off the program counter along with the register set and return back to where it was, right there. So we're looking for something along that set of events. Your best bet is just type this as a list, memorize the list of what happens in the course of that there. And again, it's in both textbooks. That's there, right there. And so, actually, I think I had a slide with that on there too. That there. So next, I think we're to our last page. No, we are done with this test. We have finished the test, right there. So, and it took me to go through and explain each one of these a little over an hour. I guess I started right at 8:30. So, but again, that's cheating. I wrote the test. I wrote this, so I obviously should know the answers. That there. But again, that if you know the answers to those 16 problems, that there, and you can answer these 16 problems and understand them, I guarantee you that you'll get at least, I'd probably say a 70 on the final. That's there. You know, somewhere in that neighborhood. That's there. So if you can't do this, then you're probably not going to do well on the final. So this is really a good indication of what to expect. That there. I haven't graded yours. I'll probably grade them sometime later this week. That there. But the grades that you saw that you did are probably not representative because you're grading. You're taking this sitting downstairs or in the canteen or in the hospital with your books in front of you and all your notes in front of you, possibly your buddy sitting next to you as a group going through and answering these questions. You know, so your grades on this particular homework assignment quiz that there really aren't representative of what you would see out there. What you need to be able to do is take this closed book that there and understand that there. Especially a couple of these where you had to look at the circuits. You have to understand that the questions there may not be the same. If you understand the questions, you'll do fine. Any questions? Does that help you understand what's going on out there? Is it harder or easier than you thought it was? Now that you saw the answers, they're always easy after you see the answers, right? That there. Yeah. Keep in mind that these short answer questions don't write too much. I have had more than one student over the years of teaching that gives me the right answer in the first sentence or two, and then writes 3 more sentences where I have to take points off because they're talking nonsense. That's there. Answer the question asked. Don't answer any more, because the chances are of you saying the wrong thing and having to lose points It's too great. You know, what is the purpose of the NMI? This is a non-maskable interrupt. It's an interrupt that cannot be masked in software or hardware. End of discussion. Don't sit there going into an explanation when you might use a non-maskable interrupt. You know, that's another question you got there. Don't, you know, if you get that wrong later on, that's fine. You at least you got that one right. That's there. So don't answer more than that there. All right. With that said, I'm going to stop this recording. Hopefully, I don't think I posted yesterday's recording. That there. Right in.